So let's have a look at our slow growing function that we have been talking about. Our aim is to get a slow growing function alpha n. And we had said that we would be doing this by taking the inverse of a very fast growing function. Isn't it? So fast growing function, and then we had defined this fast growing function that we are going to use, which was based on the Ackermann's function, and we had said that we would be making use of a function which goes like this. When k equal to 0, it is equal to aj plus 1, j plus 1, and when k is greater than or equal to 1, it is going to be given by an iterative function or iterative application of a lower level function. So it is going to be a k minus 1 applied j plus 1 times to j. We had defined what is meant by this function iteration, right? So we can just recall from the previous lecture notes if you don't have it with you. So this k is something we call as the level of the function. J is our parameter, k is our level of applying the function. So our aim is to see how does the function grow with level. We already have two lemmas to tell us that. We had said that when k equal to 1, we had a relation which said that a1j is equal to 2j plus 1. And then we had said that when k equal to 2, we have a relation which goes as a to j is equal to 2 raised to j plus 1 into j plus 1 minus 1. So these were the two lemmas which dealt with level in a certain sense. So we can see that the level makes a difference because here it is linear, or the function as it is, the a1 function if you say, it changes linearly with j, whereas the a2 function, when level is 2, it changes exponentially with j. Isn't it? So a1 and a2 have different curves or different ways of growth. So the question is now, what would k equal to 3 and k equal to 4, that is these levels, what is the impact that they'll have on the growth? Growth with j. As you can imagine, if it with a change of 1, it's going to go from linear to exponential. It is likely to grow much higher or much at a much faster rate with k equal to 3 and 4. So that's exactly what we are going to see. So what we are going to do is, for different values of k, we are going to plot ak1. Not exactly plot, we are just computing ak1s. So here the what we are taking is j equal to 1 and seeing the change in growth. So what about k equal to 0? We have a01. We know what is a01, it is 2. When k equal to 1, what is a11? We know what we are talking about, right? a11 is 2j plus 1, that is 3. Then when k equal to 2, we need to know a21. So a21 is going to be 2 raised to 1 plus 1, that is 2, 1 plus 1, that is 2, minus 1, and it is the same as 7. When k equal to 3, we can expect it to be much bigger. Now a31 is going to be a2, 2, 1, isn't it? So it is a2 into a21, and a21 is something we already know as 7. So this is going to be a27, which is going to be 2 raised to 7 plus 1, 7 plus 1 minus 1, which is the same as 2 raised to 8 plus 3, that is 11 minus 1, which is 2047, as we all know. So we can just note that from 2 it has gone to 3, from 3 to 7, and from 7 to 2047. So it is quite a bigger and bigger jumps, as we can see, right? This is a big jump, this is a small jump, this is a big jump, this is a much bigger jump. So we can expect our A4 1 to make a much bigger jump, right? Isn't that what we expect? So let us just see how big it actually is, and we'll be surprised to see that it is really quite big. So A4 1 would be A3 2, A3, just a minute, let me get that right. What is going to be A4 1? A4 1 is going to be A3 raised to 2 1, isn't it? Now what is A3 2 1? It is A3 1, and we already know what is A3 1. We have computed it. We found that it was 2047. So what is A3 2047? It is going to be A2 2047 2047. Applying something 2047 times is 2048 2047. Applying something 2047 times or 2048 times is quite a big task. So let us say this is going to be A2 done 2047 times into on A2 2047. So let us leave this big part aside by taking the greater than sign, because this itself is enough to overwhelm us. So we have this greater than A2 2047, and this greater than is a real understatement because this is much greater than that. Okay, now so this is, what is this equal to? This is the same as 2 raised to 2048 minus 1. See, how big is that exactly? It's the same as 2 raised to 2048 plus 11, that is 2059 minus 1. Now let us just make things simpler. So we'll just take a greater than 2 raised to 2058. It doesn't make much of a difference, right? Because it's all very large. So this is actually greater than or 10 raised to 516, because this is actually 16 raised to 516. So instead of 16, if you take 10, it is going to be much greater than that. So it is greater than 10 raised to 516. Now which is greater than, much greater than 10 raised to 90. And why we are talking about this 10 raised to 90 is because it is a special value, in the sense that this is the order of number of atoms in the universe. This is what it is estimated. So it means that it is a practically, or this 10 raised to 516 is a practically unimaginable number. There's no practical reason why anybody should be, or in the computing domain at least, we should be talking about such large numbers, because we are hardly going to come across them in order to do any computations of that size, in the sense that we cannot talk about 10 raised to 90 distinct objects, right? So for all practical purposes, we need not go beyond A41 is what it means. So how do we use that in order to get a slow growing function is our next thing. So we define our alpha n in the following way. We say that our alpha n for any n is defined as the minimum value of k such that ak1 is greater than or equal to n. Okay. So in that way we get a slow growing function. How slow? Let us just see. So let us just plot alpha n's. So for various n's, let us just plot alpha n and see the reason. So when n equal to 0, what do we have alpha n as? Now the smallest k that we can think about is a 0. So A0, 1, we know it is 2. So it is greater than or equal to 0. So then let us talk about n equal to 1. Again alpha n is 0. Why? Because A01 is equal to 2 and it is greater than or equal to 1. What about n equal to 2? Again it is 0 because A01 is equal to 2 which is greater than or equal to 2. How about 3? Now we have alpha n cannot be 0. Reason being that alpha n is 2 which is not greater than or equal to 3. So let us look at the next one. It fits because A11 is 3 and it is greater than or equal to 3. Now how about 4? We know that 1 is not going to fit. Why? Because A11 is 3 and 4, it doesn't exceed 4. So let us look at 2. So A21 we know it is 7 and it is greater than or equal to 4. So it fits. Now how about 5, 6 and 7? For all of them we have 2 because A21 is equal to 7. It is greater than all 3. Right? Now how about 8? Or rather how about all the numbers from 8 to 2, 0, 4, 7? We have that. It cannot be 2 but it is 3. Reason being that A31 is 2047 is greater than or equal to all numbers in the set 8 to 2047. Right? So now how about the others, numbers from 2048 onwards? In fact, we know that 10 raised to 5 and 6 comes in this and it goes beyond much more. For all those numbers, 4 is sufficient because A41 is, we know, much greater than 10 raised to 5 and 6. Right? So in that way, now if we have a look at the growth of alpha n with n, right? We just put n here and alpha n here. What do we find? We find that it almost stabilizes at 4, right? Does not grow beyond that for howsoever long we go. So that is why it is a very slowly growing function. Okay. So this is the function that we are going to use in our analysis of disjoint set forests. We find that our operations are order of alpha n, which is equivalent to saying that it is order of 4, which is the same as order of 1. So our aim is to do this, but how is it done? We'll come to in the next class. For the present, what we have seen is what exactly is alpha n. Thank you.